Okay, good evening, everyone. Congratulations to everyone who remembered to come today on a Wednesday. Very proud of you all. So we should be recording this live right now and making it available later. Ah, yes, I can see here that it is okay. I'm just going to check the sound. Recording this live. Okay. We have confirmation everything is working. So we're going to continue with a little bit of review from last time and then go into more on the same topic, really. Our laptop computers are here. At the break, you can sign one out if you need it. Just remember to fill out the sign-up sheet if you borrow one. But today will be just another nice class on types of data and ways of summarizing those data in exploratory analysis. Does anyone remember the types of data that we covered last time? What's that? Yeah. There's categorical. What else? Numerical. Yeah, we broke down numerical into discrete and continuous, and then categorical, and yeah, we've sort of lumped together categorical and nominal. Right. Nominal being it's not a number at all. Ordinal meaning that it is categorical, but it has an order, and then numerical and discrete. Very. So we're going to go over today a number of different methods for looking at all of those, which we started talking about last time. Just to review the vocabulary so far, remember the population is the entire group of interest, and in different situations, the population could be, for example, all New York City adults. It could be all people who have a certain condition. It could be everyone in the world. It could be a number of things, but it's important to understand what your group of interest is, and that your sample is a subset of that population. We'll be talking about more of these later and ways of extracting the sample from the population. And your record or your observation is your data from one individual in your sample. And descriptive statistics are the kinds of things we're doing yesterday and today, which are ways of summarizing and visualizing your data to gain some intuition of it. And I believe that descriptive statistics are an essential first step in any analysis that really matters. And finally, inferential statistics is learning something about the population from the sample, because we have incomplete data, we have measurement error, and yet in the face of all of this uncertainty, we want to infer something about that population of interest. Variable, word that we'll be using lots, is any characteristic that is recorded for the subjects in the study, and this is where we talked about those types of data, the nominal data, including binary and categorical data types such as treatment group, marital status, race. Ordinal data, which are similar except that they have an order, such as the birth order among siblings. Anything where there is a rank, and these might be also lumped in with as categorical variables, but ordinal variables have this distinction of having an order that matters somehow in your analysis of the data. And then finally, quantitative, which includes the discrete and continuous variable types, such as the number of children in a household. That would be discrete, or height, weight, and age, which would usually be considered continuous. But as I was saying, the border between discrete and continuous can be a little bit fuzzy. You can summarize your nominal and your ordinal data using frequency tables, such as these. These are the one-way tables that we made for that imaginary clinical trial involving a treatment and a control group and the level of self-reported pain. So frequency tables, contingency tables is just a fancy name for listing the number of records with each of these values of the variable. And bar plots do the same thing, just in a graphical format. Pie charts are another way to represent that same thing, but not very popular with statisticians, except that I really like this one. It's very clear what this pie chart means, doesn't need any more explanation, although the legend is still helpful. But yeah, the pie charts, they're popular in newspapers and can sometimes be nice if they still get across enough information, but they're generally disliked by statisticians because they're not as quantitative as a bar chart. Anything that you can represent in a pie chart, you can represent more quantitatively in a bar chart. And in this case, it doesn't really matter if this is 20% of the pie I've eaten or 5%. Good application of the pie chart, and much more visual appealing in this case than the equivalent bar chart. So just one more example: number of students who received an A. I don't know how many of you had cold cereal for breakfast? Come on, nobody eats cold cereal?
Not today.
Okay, bad example. How many people had hot cereal for breakfast? How many people had something out of a wrapper? Right, okay.
Yogurt.
Okay, we'll count that as coming out of a wrapper. How many people had something out of a wrapper? 1, 2. How many didn't have breakfast? 5. Okay, so there's our example. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people here. We had, was it 3 who had something out of a wrapper, and 5 who didn't have any breakfast. Then these are all equivalent ways that we could summarize that data. Sometimes the actual numbers are of interest. It matters whether, so 3 out of 13, that's a difficult divisor here. I don't know what 3 divided by 13 is. That's about, let's say that's 22%. It matters whether 22% is 3 out of 13 or 300 out of 1300. So commonly in descriptive statistics, you will include both of those. You'll have the actual frequencies and then the proportion or relative frequency given either as a fraction or as a percentage. And so it can either be used, but usually in a frequency table for publication, you would include both. If it's for yourself, up to you. And they can both be used for bar plots, either the raw numbers or the percentages. Which, I don't know, what do you think would be better to use in a bar chart? The raw numbers or the proportions? So on your y-axis in the bar chart here, what do you think would be better to use? Proportions or numbers? In this example, so in the case of the pie, that would be maybe the weight, but in this example, it's the number of students who had different things for breakfast. What would you do? Yeah?
The proportion lets you see it more consistently across the different bars, so that may be better.
What do you mean by more consistently?
Like you can, instead of just the number, you can see like what percentage. I guess if it's such a small number, you might not hear.
Yeah. Yeah, I would say, yeah.
I think it depends probably a little bit on what you want to display, but I guess percentages would make it easier for someone to look at it and have an immediate feel for what sort of split up is. Large numbers can be easier than the bars.
Yeah. Any other thoughts? Yeah.
I think in this case we can use frequency. It will have more information. We can read how many students got an A from each bar.
How many? Yeah. So you three were actually the perfect three to ask because you each gave a slightly different answer. There was proportion, there was maybe proportion, but it depends, and then there was number, and I think you're all right because these are descriptive statistics, and it really matters what you want to understand and what you want to communicate about the data. So there isn't a right answer to that question. And you know, if it were, you know, if you wanted to communicate like how many packages of yogurt were going to be needed, then it would be the number that's more important. Whereas, you know, if you're talking about percentages and preferences, then the proportions would be more important. So, so descriptive statistics are, I think, maybe underappreciated for the amount of thought that goes into them because there's always a lot of ways to present them, and how you present them affects how people will read them. And that's maybe where, you know, that's saying about how there are lies, damn lies, in statistics. I think that might be part of where it comes from because you can give a very different impression based on how you present the data. It's not the statistics or the data that are lying, but if you want to lie, you can find a way to, you know, to present things in a misleading way. That's not the fault of statistics. Statistics are going to be as honest as the person who is presenting, more or less. I mean, you have some constraints when you're dealing with numbers, but there is a lot of flexibility to decide how to tell your story and how to communicate it. Oh, there's maybe one other answer that could have been given to this one, and that is that you can do both. You can put proportions on your y-axis and then put the actual numbers on top of the bar. That's another alternative. So these are just a few graphical summaries of ways to represent a quantitative variable from the most detail to the most summarization. The most detail being showing an actual data point for every record or observation, to the most summarization where it's, I don't know, the most removed from the original data. But these plots, you're going to make them and you're going to be able to read from them these key things: the central tendency, where most of the data lie, spread, like how much variability there is in the data, skew, meaning does, from that central tendency, is there more variability towards one side than the other? And finally, outliers, if there are any single observations that are really far removed from most of the other observations. This dot plot, I feel like, is actually very rarely used. There might be some instances where it's useful, but this is basically just a histogram with the actual dots put there. It's kind of cool, but not very common. Histogram, on the other hand, is very common. This is, remember, where we took a quantitative variable and then turned it into an ordinal variable by setting these bins and counting the number of observations in each one of those bins, and then making a bar plot of the quantitative variable. When you make a histogram, it's good to remember that, again, some of your choices or the default choices of your software will affect the story that you tell with data. And the key decision you have to make in making a histogram is the bin size. Because the smaller your bins, the smaller your number of observations in each bin will be. That's going to mean that you will see more sampling variability in each of those bins because the number of observations in the bin is smaller. And the more detail you're going to see. Whereas with larger bins, the counts in each bin is higher, sampling variability is lower. So it's not necessarily always better to use smaller bins in order to see more detail, because of that extra noise or sampling variability that you have in each bin when you do this. It might actually make it more difficult to see the pattern of a pattern in the data that is more apparent when you're doing a more coarse summary. But actually, I'll mention on the other hand, it is also sometimes possible to miss something in the data by having too large of bins. I mean, it's even possible to have two peaks in your histogram that get sort of merged together if you're using very wide bins. The main things to look at when you're interpreting histograms are that the central tendency, where most of the data are. Remembering that the median is that point where half are above and half are below. The spread, how wide it is, and shape, whether it's symmetric or has more variability to one side or to the other. With symmetric distributions, this is made to look like a normal distribution, which we will return to quite a bit. It is symmetric, meaning that if we draw a line in the middle of it, it's a mirror image on either side. This is a sketch of what I would call the underlying probability distribution, or the probability of observing each outcome in the entire population. Of course, if you make a histogram from your sample, it's not going to look perfect like this because of what we call sampling variability. This, on the other hand, is a skewed distribution. This is left skewed because the left tail is longer than the right tail. And this is a right skewed distribution. And these kinds of skews happen in real life. A couple typical examples are lifespan. If you plot for all individuals born in a certain year, they would go back to 1920 and plot how old people born in 1920 were at the age of their death. You would see something like this. There might be some bumps in here due to major wars. I don't think there have been any due to any epidemics large enough to cause a bump in the overall population like this. So it would look something like this, where you have relatively few people dying as an infant, and then it increasing and being at peak at some age, and then fairly quickly dropping off after that. Whereas a classic example of a right skew distribution is income, where you have a lot of people around one income, and then can't go too far to the left from there because you can't have a negative income, but it can go very high from there. You have this right scaled distribution in a capitalist society where there's no upper limit to how much. For shape, the main thing, so there was skew is one aspect of shape, modality is another. This is a unimodal distribution, and this is a bimodal distribution. It's not always this obvious. It's obvious here because there's a lot of spread between the two modes, and because the variability of each of the mode is fairly small compared to the difference between those modes. And finally, outliers, which are those observations that that deviate a lot from the rest. And there are any number of different definitions of outliers. They're all arbitrary. Essentially, an outlier is something that doesn't look like the rest. As an aside, I wrote a whole software package based on trying to identify duplicate tumor profiles in public databases of tumor genomic data based on outlier detection. And the most challenging thing of that whole thing was trying to define what is an outlier. Because this distribution can be quite different depending on the situation. It's nice when it's nice and symmetric and normal like this, but where an outlier changes if you have a skewed distribution, and it changes depending on the width of these tails. It depends on the number of observations that you have. The more observations that you have, the more able you are to say what the main distribution is and what is an outlier from that distribution. But in exploratory data analysis, you just make some plots and identify things that look like an outlier. No mathematical definition of them, but these plotting methods will help you to find them. And when you have an outlier, you probably want to take a look and understand if there is a reason that you can identify it as to why it is an outlier. We're generally hesitant to remove data unless we can explain why we're removing it. Either because we identify, oh, this looks like coding error, it's completely implausible, or some identifiable reason why it's out that way. Otherwise, it might be something you can learn that is actually part of your population. Box plots. These are great because they are a high level of summarization that are nonetheless quite quantitative. They're quantitative because these lines in the box occur at quantitative places, the 3 quartiles, so that the difference, the width of this is the so-called interquartile range, and the middle is the median. These whiskers, as we mentioned last time, there are some different definitions of whiskers. Usually they are at the median plus or minus 1.5 times the interquartile range, or the most extreme data point, whichever is closer. So you can kind of see in this data set how it's more summarization than this density line plot provides. You know, it's less detail, but it still gives you, especially if you are start to get kind of used to looking at box plots, gives you a good idea of where the centrality is, of whether there's skew, and whether there are outliers. One more aside about box plots, and it's only an aside at this point because I'm not sure you can do this in SPSS, but one nice thing that is popular these days in box plots is to actually make a dot plot on top of it. Put all of your data points on here, overlaid on top of the box plot. So then it's both summarized and detailed. See where the individual data points are, and you can get these numerical summaries from the box. And usually there's some jitter added to the data points so that they don't fall on top of each other. Yes.
Would any value or any data point outside of the whiskers be considered an outlier? Like that?
Well, that's the convention with these whiskers, is that anything that falls outside of them is a potential outlier. I mean, it doesn't mean that it's an actual outlier, but it's something to look at.
But it would be displayed with
that. Yeah. The whiskers are placed such that this is a definition of outliers as anything that lies outside of those whiskers. Now, I can tell you that this is simulated from a normal distribution. So all of these data come from the same normal distribution. There's nothing unusual about this outlier. If you simulate the larger sample you take from a normal distribution, the more points you will have fall outside of these whiskers reliably, even though those are perfectly normal part of your normal distribution. And in fact, if you remove them, then it's no longer a normal distribution. That's an example of how in any distribution, it has tails, it has extremes. It doesn't mean that they don't belong in your sample. But yeah, good question. For box plots, anything outside of these whiskers, this is the box plot's way of identifying. One nice thing about the box plot is its quantitativeness, but its maybe bigger advantage over histograms is that it makes it easy to compare distributions by putting boxes side by side. Hi, Tony. Hi. So this example of male and female heights, it lets you very quickly see that the median is different by about, let's see, 64 to 72 inches. So I don't know, about 7 or 8 inches. And there is certainly overlap, but the central parts of the distribution are different. So those are graphical summaries. A lot of them we did already, just a little bit more detailed today. I'm going to talk now about numerical summaries of these quantitative variables. mean. This is the granddaddy of the summary statistics, and it comes up over and over. All it is the sum of your quantitative observations divided by number. So the average amount you paid for lunch is the amount you paid in total divided by the number, splitting the bill. That is all it is. This capital, this is the Greek letter sigma. This indicates a sum. This is telling me that I'm going to sum. There are observations, I indicating which observation or which individual. So this is the sum from individual 1 to the nth individual divided by the number of individuals. And if you look back to the syllabus, you'll find that we are using the convention in this class that things calculated from a sample, we're using the Roman numerals like X. Things representing the population, we use Greek letters like U for the mean. So X bar here is the mean for this sample. So things to know: the mean is not resistant, that it is strongly influenced by outliers. These are 4 different real distributions: a normal distribution, a log normal distribution. That is one where if you take the log of all the values, then it becomes a normal distribution. An exponential distribution, this means that the generating probabilities follow an exponential. This one would be an e to the minus something, so that the highest probability is at 0, and then it's just a decreasing probability to larger values. And a uniform distribution. This is uniform between -2 and 2, meaning that any value between -2 and 2 can occur with equal probability. These are 4 different continuous distributions, one bounded, actually 2 are bounded. The exponential has a minimum, the uniform has an upper and lower bound. The other 2 are, actually tell me, is the log normal bounded or unbounded? I will put this on the test, but just, you might as well know what a log normal distribution is. It is bounded at the bottom, because it's the distribution where if you take the logarithm of it, it is a normal distribution. So then, the log of it is unbounded between -infinity and infinity. That's the normal distribution. But then you take the exponential above that. Exponentials are always positive. Yeah. So this has a lower bound of 0. So we have 3 bounded and 1 unbounded distribution. Yes.
Probably a dumb question, but those are 4 different, if not all the same data and different.
Oh, these are 4 different, let's say, these would be 4 different variables. Yeah. Each drawn from a different underlying population distribution. So this would be maybe something like heights, this something like incomes. I don't know what exponential would be like. Maybe that could also be something like incomes and uniform. I can't think of examples off the top of my head. Certainly there are in practice things that are uniform distributions. But I can't think of it. But the point here is, so on top of each of these box plots, I put in red the mean. And so you can easily compare the mean to the median and to the interquartile range, or this central part. And for the normal distribution, the mean is right on top of the median and right in the middle. For the uniform distribution, that's the case again, very close. But for these two skewed distributions with these outliers, like lots of data points that fall outside of the whiskers, the mean is fairly far from the median, at least with the exponential, where the outliers aren't too extreme, or the skew is not too extreme. It's a little bit away from the median, and here where we have really extreme skew, it's very far from the median. So actually, it's kind of an interesting take-home lesson from this is that just by looking at those two numbers, the mean and the median, you can tell if you have a skewed distribution or some extreme outliers. If there's very much difference between the mean and the median, say compared to the standard deviation or the interquartile range, you know that this is not a symmetric distribution like the normal or the uniform. So the median is just the midpoint. So if you have an odd number, then the median is your middle observation. If it's even, well, this is one way to calculate it, the average of the two middle observations, as just a very slight heads up. For small samples, there are actually different ways of calculating the median, and including things like estimating the distribution and interpolating. In R, they have like 9 different options for how to calculate the median, including you can say, I want to do it like SPSS. You can specify like other software packages for compatibility so that you get the same answer as other software packages. It doesn't really matter, but if you happen to find that some of you are using SPSS and some of you are using R to get different answers for a median when there are only like 4 observations, that's why, because they're using different algorithms for calculating. So, examples. This is pretty easy, but the main point here with this odd number of observations is that the median in these first two does not change whether the last number is 5 or 100 million. So median, on the other hand, is robust to outliers. It's resistant. Those were dwarfs. Instead, it would be the middle dwarf. And again, it's resistant to outliers. So finally, the mode is just the value that occurs most often. So it's really only defined for categorical variables, but we still describe continuous distributions as unimodal or bimodal according to the highest bar in the histogram. So for a categorical variable, that's no problem. You make your bar chart, the highest bar, that's your mode, end of story. But with the histogram, of course, it depends on the width of the bins that you use to summarize the data. So the modality or the mode could be is not as well defined for a continuous variable from a sample. Anyways, if we actually have the population distribution, we know where the mode is. We know if there are multiple modes because we have a continuous probability distribution. What do you think? Is this Unimodal or bimodal? Yeah.
What is it? Bimodal?
Bimodal?
It's two, it's almost.
Here and here?
Oh, no. I was looking at the other two that
Here?
look exactly this.
Yeah, it's hard to know, right? It's like this could be
Yeah, those two.
this could be another mode, or this could just be, you know, part of a single distribution. It's also kind of hard to know here too, because this is a small sample size. What is this? This is only 6 here. So if we had 10 times the sample size and this were 60 and this were 40, then I would be pretty confident that these were 2 different modes and this was bimodal. But with a small sample size like this could very easily just be sampling error from a unimodal distribution. But in our sample, that's the mode. As I mentioned, you can infer skewness from that difference between the mean and the median and the mode. The difference, how big that difference is, and which is larger. The mean is the one that gets skewed away from the mode and the median. So if you have the mean being larger, that's a right skew. The mean being lower, that's a left skew. Now, percentiles, the definition of it, I know you've all heard of it, but it is the value such that P% of the observations fall at or below that value. And you will be using this lots for calculating so-called p-values and for calculating confidence intervals. That is the key thing, is that it's the value at which P% fall at or below that value. So this is the Pth percentile, this is the 90th percentile, where 90% of the distribution is below and 10% is above. Quartiles are, we've covered these before, but they're more, so consider those introductions as we were talking about box plots and that. Here are the definitions. The quartiles are what split your data into 4 equal parts or 4 equal probabilities, meaning that the probability of an observation of this continuous variable is equal in these 4 different bins. So that the 25th percentile, the 50th percentile, the 75th, well, this would be the maximum here. So the quartiles would be defined at the 1st, the 2nd, the 3rd quartile. We don't talk about the 0th or the 4th quartile. They are, well, the 0th is your minimum, and 4th would be your maximum. We have other words for those. Speaking of max and min, the range is the difference between the maximum and the minimum values, and it is another measure of the spread. So the range. So we have now interquartile range, and we have the range. Say range is a resistant measure, that is, it's resistant to outliers. No, it's in fact, it is in fact a very sensitive measure. And unlike something like the mean is not resistant, but the mean at least will stabilize as you capture larger and larger samples. It will converge to the same as the population mean. Whereas the range will never converge unless you have a bounded distribution. For that uniform distribution, the larger the sample you have, it would converge to the true range of -2 to 2. But for an unbounded distribution, your range will never converge. The larger the sample you take, the larger your range will get. So that's something to keep in mind when you think about the range, is that it depends on your sample size, or it is affected by your sample size. If the range is not defined in your population, like a normal distribution where the range is from -infinity to infinity, then it will never converge in your sample. You got that? So for a bounded distribution, your range will converge to those bounds for a large sample, but for an unbounded distribution, your range will never converge. I just try to hammer that home because it's easy to lose track. When you're dealing with a sample, it's really easy to lose track of the fact that this is a sample from a whole population, and to remember the extent to which the things you observe on your sample reflect the population or do not. The range is something that does not reflect the population, particularly for an unbounded variable. Variance and standard deviation also measures of spread that we calculate from the squared deviations of each observation from mean. And unlike the mean, where we divided by n, when we calculate the variance from a sample, we divide by n minus 1. So if it is the variance for the population, it's divided by n. It's the variance for a sample, it's divided by n minus 1. N minus 1 is the number of degrees of freedom involved in calculating this statistic, something else that we'll be returning to. To give some intuition for why this is required to get an unbiased estimate of the variance. An unbiased estimate is one where if we continue taking samples of the same size, take 1 million samples, calculate the variance on every one of them, then we take the mean of all of those variances that we calculated. How do you expect that mean to compare to the population mean variance? Tricky question because I'm talking about mean variance so many times. But does the question make sense? Okay, so the question, first we have a population. Let's say the population is adults of New York, and we know from the census what the mean and the variance in that is. Okay, so the mean is, I don't know, 70 inches, and the variance is 10 inches, just for example. Now, we take a random sample of 5 people, we calculate its mean and its variance. That's our sample, just 5 people. But then, so first with that 5, we calculate the mean and the variance. We want that mean and that variance to be the best estimate possible of what the mean and variance in the population are, right? We're not going to make an intentional error that makes either of those larger or smaller. There will be a certain amount of variability that's unavoidable because we only have 5 people, but beyond that, we don't want to be any more wrong than we have to be. So if we're not any more wrong than we have to be, you would expect that if you were to repeat the same study over and over, that on average, you're correct. That the mean that you calculate and the variance that you calculate for those little samples, on average, are correct. Like they're centered. You know, if we looked at what's a nice Yeah, that if we calculated the mean every time, we might get something that looks like this, distribution of means, but that this middle of them would be equal to the true population mean. And the same thing for the variance, that middle is equal to the true population variance. We'd be pretty annoyed if actually the true population variance was always over to the right. You wonder why you're calculating it this way if you know that you're always biased to one direction. And that is why it turns out that you have to divide by this n-1. And the intuition that maybe I can give you about it is that this x bar, this mean, is calculated from your sample. And that mean is right where it minimizes this sum of squares. So regardless of, in this fact, that the true population mean is 70 inches, this is calculated from our sample in a way that minimizes the variance. So if you didn't do this, you would always be underestimating your variance because you're putting your mean in the place that minimizes the variance. So your variance is wrong if you calculate it from a sample where you estimated the mean from your sample. And this correction for the degrees of freedom used in calculating that mean turns variance into an unbiased estimate of the population variance. Does this make any sense? So if you actually knew the true population mean, but you were calculating the variance of your sample, you wouldn't have to divide by this n-1, because you're not using any of the degrees of freedom of your sample. You're not using your sample to optimize your variance. So going back to these four distributions again, I plotted here the deviations from the true population mean in each of these. I know what the true population mean is because I simulated the data. These are the deviations. These are the squared deviations that go into the calculation of the variance. So remember that for the mean, we were just adding them up like deviations from 0 and dividing by n. And you can see, that some of these outlier values in the log normal are quite a bit away from the rest. But once you square them, that's even more extreme. Like in this log normal, this furthest outlier point just like dwarfs most of the data. So the variance and the standard deviation are even less resistant than the mean is. The mean, is somewhat susceptible to outliers and to skew, but then the variance is even more susceptible because you're squaring these deviations and making any outlier a squared outlier. Some things to know about the standard deviation. That's the square root of the variance. It has the same units as the observed variable. So if height's in inches, the standard deviation is also in inches. It's a measure of the spread that is always positive. It's only 0 when every single observation has the same value. As soon as you have any difference in your values, then your standard deviation will be greater than 0. The more difference you have between them, the bigger S gets. So on top of this plot now, where I had put before the means, I've also added the standard deviation so that you can see on the normal distribution, the standard deviations are pretty close to the interquartile range, which is kind of convenient. So it's like when the when you have a normal distribution, your box plot kind of shows you this first one. This is the 1 standard deviation, and then I put in the dashed line at 2 standard deviations. So the box plot kind of corresponds to the mean plus or minus 1 and 2 standard deviations for a normal distribution. But for the log normal distribution, you see that the shape of the box is not all that different, but the mean and standard deviation are even more off. So remember how the mean came up quite a bit to this 3rd quartile, but the standard deviation is huge. You know, because it is so sensitive to skew. So if you have something that you believe is from a normal distribution, or you have enough data or experience to know that it's roughly a normal distribution, then the mean and standard deviation are absolutely the way to represent it, because they are the parameters that describe a normal distribution. But if it's not normal, if it's log normal, it's something else, and you want measures of spread that are not so sensitive to outliers. These are some alternatives. The interquartile range, that's the width of your box, or something called the median absolute deviation, or MAD, which is the difference between each observation and its median, and then taking the median of that. And then again, there's the range, which of course is not robust to outliers or to skew. So here's a summary. I won't go over it all again, just so that you can remember what all of the things that we have covered in this class, things that I'm considering important that you know going ahead and on the exam, and also your learning summary for the class. And that is just about the most well-timed lecture I've ever done, right?
You're getting out before the air conditioning goes on.
Right. Yeah, I'll let you sweat it out up here.
Hopefully, yeah, it's not quite 6 o'clock yet, so we still have hope that it'll stay.
Yeah. Any questions? I'll just stop screen sharing first. Any questions? Yes.
Do you recommend that we do the exercises in the reading that are in like 1.9 and several pages? Good
question. If you want practice, either like practice with the software, or you just don't feel that comfortable with the material, then yes, like they're nice exercises for giving another perspective and for having solutions. You don't have to. We pretty carefully keep the exams on the topic of what we've covered in lectures plus assignments and labs. So I would say they're a good resource to have if you're not getting the concepts yet. And these are important. I mean, everything is going to build on these. So if you are not feeling confident and have the time to do something extra, it's time well spent.